For years, interacting with artificial intelligence has operated like a relay race. You pass a prompt to a model, it runs a quick computation, hands you back an answer, and immediately ends the interaction. This is the standard stateless API request and response cycle. The system spins up, generates text, and spins down in a matter of seconds. That architecture works perfectly for answering a discrete question or drafting an email. But if you assign a task that requires monitoring a database for hours, reacting to shifting variables, and executing a sequence of conditional logic, a system that resets every few seconds simply collapses. Solving this limitation requires moving away from isolated conversational bots toward autonomous long-horizon agents. This demands 24/7 stateful environments. Instead of a ping that dies immediately, agents require an unbroken timeline spanning multiple days. By maintaining active state on cloud virtual machines, the system preserves context. It remembers tasks from 12 hours ago, applying that knowledge right now. Transitioning from a stateless, ephemeral cycle to a permanent, stateful architecture is the strict technical prerequisite for any multi-day autonomous workflow. Keeping a system running continuously is only the baseline. The true engineering bottleneck is ensuring that a long-running agent does not hallucinate, drift from its objective, or encounter a fatal error while operating unattended. Solving this requires overcoming 3 distinct hurdles. First, compute orchestration, universal tool integration, and deterministic transaction safety. Google recently announced a unified agentic stack built specifically to clear these 3 hurdles and standardize how agents operate in the background. To understand how a system can safely execute complex operations while you sleep, we have to map the 4-layer architecture of agentic commerce from first principles. Mastering this specific stack is necessary because it allows developers to abandon brittle, bespoke API pipelines and build on a globally standardized framework. Layer 1 of the architecture is compute and orchestration. Here is where the raw logic processing occurs. The practical implementation of this layer is Gemini Spark. It is an agent running persistently on dedicated Google Cloud Platform virtual machines, entirely decoupled from your local hardware. This layered system graphic illustrates how the base model capabilities are separated from the orchestration wrapper. At the core sits Gemini 3.5 Flash. Flash serves as the high-speed inference engine, optimized specifically to read and write the logic required for agentic workflows. Surrounding that core is Antigravity 2.0. This is the state management harness that dictates exactly how and when the inference engine is deployed. When a user assigns an overarching goal, Antigravity parses that request and breaks it down into directed acyclic graphs, or DAGs. These graphs map out complex logic sequences. The harness forces the model to execute the graph step by step, evaluating the outcome of one node before proceeding to the next. To ensure developers can monitor this logic, Antigravity includes open telemetry tracing directly inside the harness. This tracing provides complete visibility into step-by-step session execution, allowing engineers to audit exactly why an agent chose a specific path in the graph. Because this orchestration occurs on the cloud infrastructure, the harness ensures the agent does not drop tasks or lose state when the user closes their laptop. It quietly runs the background processing loops, advancing through the graph over a period of hours or days until the final condition is met. Structurally separating the base LLM from the orchestration logic is what prevents the model from wandering off task. The harness provides the rigid tracks, the model provides the engine. Once an agent has a stable runtime, it needs access to external data. To check a calendar, read a document, and update a database, developers traditionally had to build custom point-to-point integrations for every single service, resulting in a fragile web of APIs. Layer 2 solves this through universal tool integration, relying on the Model Context Protocol, or MCP. This diagram shows the efficiency of the protocol. A single central server implementation replaces custom end-to-end API coding. By implementing one MCP server, a developer's tool becomes immediately accessible to any compliant agent on the market. Whether it is a cloud-managed agent like Spark or a self-hosted local agent like OpenClaw, they all communicate using the exact same standard. Standardizing the interface layer eliminates vendor lock-in. Developers write their tool integration once, and the entire ecosystem of agents can interface with it securely. Orchestration and tool access allow an agent to gather information, but managing the risk of autonomous financial actions introduces an entirely new complexity. Before an agent can make a purchase, it needs a highly controlled staging ground. This is the universal cart. This staging area pulls in data streams based on your activity across Search, Gemini, and Gmail, compiling the items you are evaluating into one unified environment. It achieves this interoperability using the Universal Commerce Protocol, which acts as the underlying communication language for retail inputs. Once an item enters the cart, the system uses Gemini models to operate proactively in the background, treating the cart as an active research environment. The cart continuously tracks price history across different retailers, waiting for optimal buying conditions. If you stage hardware components from multiple vendors, the cart actively flags product incompatibilities and surfaces viable alternatives. By applying intelligent reasoning to the staged items, the system anticipates logistical or technical conflicts before the checkout process even begins. The decision-making logic also factors in your Google Wallet data. It automatically evaluates your available payment methods, calculating loyalty perks and merchant offers to uncover hidden savings without manual input. When the optimal conditions are met, the Commerce Protocol packages the staged items and delivers them securely to the final merchant of record for payment. By combining active inference with standardized data protocols, the shopping cart evolves from a static holding area into an active, intelligent pre-transaction environment. All of this staging leads to the most critical technical hurdle, allowing a software system to close an irreversible financial transaction without human intervention. Layer 4 handles this execution. It is governed by the Agent Payments Protocol, an open standard recently donated to the FIDO Alliance to ensure platform-agnostic security. Look at this data payload attempting to pass through a payment gateway. It is halted by a cryptographic guardrail called verifiable intent. This creates a tamper-proof digital mandate. The gateway strictly prevents execution unless the agent's payload perfectly matches the pre-authorized spending criteria and brand restrictions set by the user. By enforcing cryptographic validation at the moment of purchase, the Agent Payments Protocol creates absolute deterministic accountability for probabilistic model actions. Let's trace a single action through the fully constructed 4-layer architecture of agentic commerce. Step 1. An external trigger, like a limited product drop, wakes the dormant anti-gravity harness on the cloud. Step 2. Gemini 3.5 Flash evaluates the trigger against the user's standing instructions and processes the logic to buy. Step 3. The universal cart stages the purchase using the Commerce Protocol to communicate with the retailer. Step 4. The cart detects a shipping conflict, flags it, and recalculates the data payload to match an alternative authorized vendor. Step 5. The finalized transaction payload requests execution from the payments layer. This architectural stack transforms the large language model from an isolated text generator into a system capable of executing verifiable financial transactions across the digital economy.